Hey everyone, how are we doing? Just got the intro music. I was playing the intro music. I was like, oh yeah, I'm streaming. What's going on? Let's get the stream over here. Vincent, great to see you. Let me pop over to the main stream. There we go. Vincent says, hope you had a good Thanksgiving. How many hours of Mulix do you need? Oh, yeah, you might be getting close. Vincent, check your points. I'm gonna throw you some extra points. There we go. Got things organized right now. Check your points, Vincent. Let's throw some more points. We got to well, I don't want to, Mubot's still here. He's here in the background. So check out your points, Vincent. It's 50,000 to get it. Let's throw out some extra points right here. I've been doing a lot of organizational stuff today. So Mubot will tell us you're getting close. Show up to the Kahoots and stuff. You're getting close. Next class is going to be a big one too. Show up to the Kahoots. Show up to the classes. You're getting close. But yeah, it's a bigger jump each time. So I think it worked pretty well this semester because we have each week we have 15 weeks. So there's 2.5 hours of classes a week. Then there's office hours. But if you just show up to class alone for the 15, generally I want people to reach it within that 30 hours. And just I throw out different amounts of points, and it just changes as the semester goes. And I throw out more points towards the end because then I want people more engaged. Well, Vincent, if you have any other questions, let me know. I've been chatting it up on the Discord. People have seen that the Statual 1 got bonus. It was approved. 320 is asking some questions. Oh, people are putting the, do you know if you are teaching class during, might be. Wilson's asking about classes during the summer. Might be, usually I teach Statual 1, BS 320, and BS 474. We might do time series again this summer. I'm meeting with my department head tomorrow. No, Thursday. And I'll ask about this. Yeah, we start setting up the summer teaching here pretty soon. But figuring that out, getting the summer teacher going. Let's take a look here. Just replying to as many. The characters would have to be factors since they are levels. Awesome. Good stuff right there. Great stuff. Sometimes the replies are a little bit quicker. But no, lots of different things right here. Someone tagged me over here. Oh man. Whoa. Last up. Oh my god. Ay. I have no idea what's going on. I don't even know. But Vincent, if you have questions, let me know. I'm just keeping up with the Discord right now, seeing what questions there are. Looks like people join some calls. People talking about some fantasy football. People talking about sports. But no, good stuff. Like overall, the Discord, people talking about different ideas for the Discord, and we want to keep the Discord nice and strong as we go into the next semester. So we really appreciate everybody who's been helping out, making the Discord really awesome. Let's find out. Oh, someone tagged me in a Discord thing. Gaming. Did Shiv say who they? Good stuff. Colin, so good to see you. Thank you so much for the pixie dust. Here's your points, Colin. Colin, we were talking about Disney. Chapter, which quiz question do you want, Lauren? Of course, Lauren. Thank you for being here. I've still got top chat on. Lauren, mention a quiz question. We'll start it up right here. Colin, we were talking about Disney. I'm gonna be talking to some students from high school via Teams, not YouTube. But I'm gonna talk to them, and we want to get them, excited about doing stuff with analytics. Like, hey, you could work for Disney. Like, I'm not saying I love working for UT, but Disney's kind of a cool company too. Now that UT is a company. Newspaper headline. Yeah, let's go to newspaper headline. You got it, Vincent. Of course. This is your guys' time. I was replying to some all the different messages, every message. But helping out. Sometimes I do that usually here in the background. Like, well, since it was a little bit slow, I was doing that. But that's usually between classes. I'm trying to get to every message. But the really great thing about the Discord is people are, replying to each other, answering questions. The one that talks about injuries, the war and the injury, right? So we've got the newspaper headline and let's see here we got. So Vincent said the newspaper headlines. So let's get the newspaper headlines. We're going to go listen to this real quick. So there's two war stories. There's one that says includes many details. There's one that says reports many details. Yeah, thank you, Colin, right there. And Colin, we need to set up the thing with... That one's too cool. We need to set up the thing where you can speak to the business analytics, the Disney Analytics Society. We'll start out here with some newspaper headlines. Let's go check it out. Disney is pretty awesome. Thank you to Disney and everything. Like, so cool. We've got people working for Disney, Riley and Colin right there. So we've got right here newspaper headlines about what happened with a Titanic back in the day. Is there evidence of a significant difference between the proportion of males and proportion of females who survived at the 0.005 significance level? So who can tell me this is their what when they're running this test right here? Now, when they say the significance level, they're telling you they're running the test using a certain what. Like that 0.005 is their what? Level of significance. Yeah, I wanted to make it happen. Definitely. And they should. They're pretty good these days. That 0.0005, not 0.05 this time, is their what when running this test. That is their something level. It's level of significance, but we usually just use a word for it, like a Greek letter for it. Not mu, like Mewtwo, but starts with an A. That is their alpha level. So they're saying they have to get a p-value below 0.005 to see if there's significance. Now, the null hypothesis here is going to be that there is no relationship, or not associated, they are independent. Somebody's survival on the Titanic was independent of their gender on the ship. Let's see if we got the next one right. So then the alternative is going to be that it's associated. So either there's nothing going on here, independent, just doesn't matter, rock.
It doesn't matter.
If you're male or female, the probability of you living or dying is going to be nearly identical. Like the differences would just be due to random chance. But the alternative is that there is an association. Like, okay, if you know someone's male or female, that would have a lower or higher probability depending on whichever one they are. So that's going to be our null and alternative. The easiest way to write it is that they are independent is the null and they are not independent, but that does mean the same thing as saying associated. So they're trying to trick you right here. Next right here, we have, are the conditions satisfied? So the conditions are going to be satisfied right here because it's like, are they random? Maybe. Let's see right here. The data in the groups are independent and they have at least 5 observations. Yeah, so this is going to be the one right here. I don't like the way they write it out. Condition 1 is random. Condition 2 is less than 10%. Condition 3, good to see you here, MK. Condition 3 is expected cell count greater than 5, which we could check that, but it does pass. And condition 4 is we have count data. Don't love the way they wrote this out. They mentioned the count data. They're mentioning independence here for like randomization. And then they're saying, I wish they said expected cell counts. That should be it right here. You don't want them to be dependent. That would be not random. Now they jump straight to the chi-squared test statistic, and this is where we're going to need to take our data, copy to clipboard, and copy right here. So copy your data. We're then going to go and bring it over to Jump. So I'm going to go over here to Jump, and in Jump, you want to go to File, New Data Table. File, New Data Table. I'm in a new data table now. Now don't click in it. File, New Data Table, and then go to Edit, Paste with column names. Edit, paste with column names. So once we paste in the column names right here, we get males and females, and we get the amounts and whether they lived or died. We're going to go over here to Table and then Stack on the table. So when we go to Table Stack, we're going to take the female column, stack it on top of the male column right there. It's just going to take both these columns and stack them. That was Tables Stack. Then we're going to click OK. So now we get a new data table here. With good to see you here, Griffin. Great to see you. 400 points for Griffin joining in. We got right here whether someone lived or died in their label. And that's our new table. And we're going to go here to analyze fit Y by X. With the analyze fit Y by X right here, and Griffin's at the top level. Great job, Griffin. We're going to run the variable right here. We're going to see if somebody's label can explain whether they lived or died and put the data in here to the frequency. And go ahead and click OK. Let's go ahead and do this. So there's what you want. Make sure to put the data. If you don't put the data, you won't get the right results. Here's the results, and wow, look at this. So the males were way more likely to die than the females on the Titanic, and I think they're kind of running with Titanic data here a little bit. But you can see right here, the chi-squared is ridiculous. The Pearson is the sum of all the cell chi-squareds. So if we had done this by hand, we would first go through and find out all the expecteds, which is a lot of work. So we would have to go through here. We'd start off with the counts, which how many observations there are, which we saw originally. Then we'd take and do row total times column total over grand total to find all the expecteds. Then from the expecteds, we would do observed minus expected squared over expected to get all the cell chi-squareds. And once we get all the cell chi-squareds, we sum them up to get the Pearson chi-squared test statistic. And I do want to mention this. Please check out today's earlier video where we walked through, and we did it here, I think. We walked through and did a full test by hand, finding the expecteds, finding the cell chi-squareds, and finding the Pearson chi-squared test statistic and plot it out. So if you want to see a full example from start to finish by hand, where we go through each concept, check out earlier video today. And there's the Pearson chi-squared test statistic of 611.205. And that's the sum of each of these cell chi-squareds. 330 plus 95 plus 143 plus 41 is 611. So 611.205. 611.205. So 205 rounds to that. Be very careful. And the p-value is 0. Now, it's going to look like 0.00001, but that's basically 0. It's got a ridiculous amount, an insane amount of decimals on it. It says e to the negative 135. That's 134 decimals after that leading 0. So that's insane. If you hover over the star, you get to see how many decimals there are. So definitely we are going to do what here? We are going to reject the null hypothesis. This is extreme evidence. It's clear to see by looking at the graphic alone that there's a very strong relationship. Now, we do want to run the statistical test because it matters on how much data we have. You can't always look at the graphic. But at this point, with a sample size of 2,000 plus, the graphic's showing this big of a deficit of a difference between the groups. And that's like a discrepancy right there, I should say. How did we get, did you see the part where we put it into jump? So we went to the analyze fit y by x, and we put in the variables right here. And with our variables in jump, once we do this right here, we run the test. Yeah, this by hand would take quite a while. You could do it by hand. I would not suggest doing it by hand. I'd suggest knowing how to read the output right here. So jump's going to be the way easier way of running this. Like doing it by hand, you have to calculate all the expecteds, all the cell chi-squareds, sum the cell chi-squareds. And the good news is this chi-squared test statistic is so large that the p-value here is 0. And that means we reject the null hypothesis. There's very strong evidence. So this is extreme evidence for the alternatives. Does that make sense, Vincent, right there? This one is 10 times easier in jump. Doing it by hand is a lot of calculations. So I do suggest if you want to work this problem by hand, which it would just take another 10 minutes, I'd say, to work by hand, is to go through and calculate all the expecteds by hand, calculate all the cell chi-squareds by hand, sum all the cell chi-squareds to get the chi-squared test statistic. So this one can be done by hand. Just make sure to carry decimals because you'll be dealing with a lot of decimals as you go between these equations. And we did a question very similar to this earlier where we did the chi-squared test of independence. How's it looking, Vincent? Your thoughts? This problem we did earlier as a practice problem was really great. It was in the morning office hours. So check out the morning office hours to do a practice problem and follow through the steps and be like, okay, now that I have my observes, I'm going to find my expecteds. Now that I have my expecteds, I can get my cell chi-squareds. Now that I have my cell chi-squareds, I sum them up. And from summing them up, I will find the chi-squared test statistic and plot it to find the p-value. Just really good practice on these right here. And I think Lauren wants the one on the particular war story that talks about injuries. So let's start up the next question. So we have the war story on injuries. War story on injuries. Let's go check this out. There's 2 of them. So tell me if I get the wrong one right here. There's 2 war stories on injuries. Awesome. Great job, Vincent. Right there, 100 points. Vincent, great job. Excellent work. Check out the video and you got it, Vincent. You got this. So we got a certain war story describing several weeks of a long war, including many details of injuries and outcomes. The accompanying table summarizes 159 recorded injuries from which both the injury site and the outcome are provided. So the easiest way to talk about this is just say injury site is independent of it being lethal. So let's just see right here. That's the null. Remember, the chi-squared test of independence uses the null that they are independent. So homogeneous. No. We're doing independent. So the 2 are independent is the null, and not independent would mean if you know where someone gets injured, that would give you information about them dying. Just think, you get injured in the head, bad. You get injured in the arm, not as bad. So we're going to need to find our expected values now. So this is if there's no relationship. And I just want you to think about how this works. We can see right here that more people are dying when they're hit in the head. So these are the people, 65 people had a fatal injury when they were hit in the body. 46 people had a fatal injury when they were hit in the head and the neck. Only 2 of them did not die. But the people who were hit in the limb from the war, 25 of them did not die, and 15 of them did die. I mean, it was like war where they didn't have good, getting injured anywhere could lead to fatality. So this right here is where I really see some big differences. The body and the head are not good places to get injured with this table. But if we were to do the expected amounts, the amount of people who are dying, if you look at this, is about, I'm trying to figure it out. So it's about 1/6 of the people, or 1/6 of the people survive. So I'm just doing some quick calculations right here that 33 out of the 159 survive. So that's 1/5, closer to 1/5. 1/5 of the people survive. About 20% of people survive. So if 20% of people survive, going off of that, if there's no relationship, I'd expect 20% of these people to survive. But if you notice 20% of them didn't survive, it was way more. This right here is way more. It's actually 62.5%. A lot of these people survived, way more than 20%. Fewer of these people survived, only 2 out of 48. And that's what this test is doing. They only say only 4% of these people survived, where we expected 20% of them to survive. It doesn't matter right here if someone gets injured in the body, the head, the limb, because if nothing's going on right here, 20% we'd expect to survive for all of them. So what we actually need to do right here is do row total times column total over grand total. And let's show how this works. To find an expected value, the formula is row total, and you get this on the formula sheet, times column total over grand total. But it works the following way. Row total, column total over grand total. And this is for this particular cell. So this would be how many people we would expect to have a non-fatal injury who got hit in the limb. So we just solve this out right here. We go ahead and we solve this. And we do 40 times 33 divided by 159. And we'd expect 8.3, which is weird to think you'd expect a decimal. But that's how many we would expect, 8.301. It probably wants to 2 decimals. 2 decimals, 8.301. Now you could go through and do this for all of them, but we're going to copy the table right here. Table, copy to clipboard, and let's copy that table. Copy, copy, copy. And let's go down here to jump, and we're going to go to File, New Data Table. Make sure to open up a new data table. New data table opened, and then we're going to full screen it. Don't click inside of it. We're going to go to Edit, Paste with Column Names. Edit, Paste with Column Names. This is going to put the column names at the top right here, so we have column names. Good stuff. Pause right here. And now we're going to go to Tables, and we're going to go to Stack. This is going to take the 2 quantitative columns, the fatal and not fatal, and we're going to stack them on top of each other. So once you're here under Table Stack, you want to click the 2 quantitative columns, which are fatal and not fatal, and then we're going to click OK. So we have both quantitative columns in these stacked columns. Don't include column 1. Double check you got this right here, and we're good to go. Now we have a new table with 2 categorical variables of site of injury and the label of whether it was fatal or not. You could change the names of these. It doesn't matter so much.
It doesn't matter!
We're going to use them anyways. And then we have the occurrence of the observations. So we've just kind of reorganized our data so we can analyze it. Let's go here to Analyze and Fit Y by X now. Analyze, Fit Y by X. And with Analyze, Fit Y by X, we're going to take, and I might switch this. Think about that there. And then make sure to put the data down here in the frequency. Probably the biggest error I see is people forget to put the data in the frequency. Let's see if this is the way I want it, because I want it to look like the table we have. And let's click OK right here. So make sure you have this. And is this the way I want it? Fatal, not fatal, I think is on the wrong side. Hey, Harper, great to see you here. Ask any questions you have. I'm going to rerun this real quick with redo, relaunch, and I need to switch these. I was wrong about the way they went. I was wrong. It's rare. Happens more often than not. So you'll see right here we have label and column 1 right here. So this is going to make our table organized the same way as the previous one. It won't affect the values, but it'll just be easier to input. So use this version right here. And now we can see that we get the same sort of output. And let's take a look over here. It's formatted the same way with the fatal, not fatal, the body, the head, the limb. Oh, that's totally fine, Harper. You got that, yeah, lowercase p account, right? So totally fine, Harper, no worries. So we're going to go here and look at the counts to make sure we get the same count values. The counts are how many you observed, meaning it's count data. Harper, if you have any questions, let me know. So there's the count data. And there we go. There's the observations, the count data. Oop, don't you do that. So there's the count data with the Good. And so now we need the expecteds. The expecteds are, remember, we already found the bottom right one right here, which was like 8.30. So now we need to go in here and go to expecteds. And you see there's that 8.30 we calculated by hand. And I know it took a while to get this. So you might say, well, it took so long to get this. Why don't we just do all the work by hand? We could. It'll help us out for the next one, though. And if I make a typo, we lose. I am just making sure I don't make a typo right here. Putting in all the expected values. Could you do how to find the degrees of freedom and jump? I am on 19 on the homework, the epidural. So when we look at this right here, how many degrees of freedom does this table have right here, Harper? Good question. Can you tell me for this one, how many degrees of freedom does this problem have? We can see the answer down below, but how many? That's a comma. Ooh, students have emailed me about that. I've had that problem. How many degrees of freedom would this have? So Harper, good question right here. How many degrees of freedom does this test have right here? It's all right if you say you don't know. How many degrees of freedom would this test have? So the formula is rows minus 1 times columns minus 1. So how many rows are there? And how many columns are there? Be careful because you don't use the totals. So how many degrees of freedom would this test have? So this test would have how many degrees of freedom? It would have 2. Great job, Harper. 100 points right there. You are right because there's 3 rows and 2 columns. So it becomes 2 times 1. Does that make sense? So the answer is it does have 2 degrees of freedom. You are correct. Great job. Good practice right there. So 3 rows, 2 columns. You have a 3 by 2. Reduce each finger down. So you now do 2 times 1. The formula is rows minus 1 times columns minus 1. But always think, okay, this is a 3 by 2. And then just reduce down. And each hand drops by 1. 3 by 2, 2 by 1. Once you know it, nice and easy on these to find the degrees of freedom for the chi-squared. You can also see this is a 3 by 2 over here. What do we mean by 3 by 2? 3, 1, 2, 3 by 2, 2, 3 by 2, 2 times 1, 2 degrees of freedom right there. Great job. So I think the epidural one's 1 degree of freedom. Double check, buddy. 1. Because it's a 2 by 2. 1. Does that make sense, Parker? 2 by 2. Mm-hmm. Does that make sense? I think you see it. I think you'll get it right now. You got it. You got it. Good stuff, Parker. Compute the chi-squared test statistic. So this is where it would take a lot more work. It is 1. Yeah. So we'd have to get all the cell chi-squareds. We did a problem earlier where we went through this all by hand. These are all the cell chi-squareds. To get a cell chi-squared, it is observed minus expected squared over expected. So you would take the observed of 16 minus the expected. I'm just finding this one right here, this cell chi-squared, minus the expected. And then we square that, and then we divide by this right here. And that is the... I think my brain broke. Let me try again. Observed minus expected. Square that. Divide by expected. I think I divided by the wrong one. I divided by the chi-squared. There we go. Observed minus, you're welcome, Harper, anytime. Observed minus expected squared over expected is the formula for each cell chi-squared. Then we take all the cell chi-squareds and we add them up to get the chi-squared test statistic. So all of these, this 1.3, this 5.1, 1.66, every one of those added up is 56.95. Type a whole number. Really? Oh, degrees of freedom. 2 decimal places for the chi-squared, 56.95. Now, the p-value for this is going to be, well, we need the chi-squared degrees of freedom. 2, we just talked about that a little while ago. Review back if you didn't hear us talking about it. And the p-value is going to be 0. It says 0.00001 right here, but that's, if you hover over it, you can see it's a lot of zeros. You have to kind of swivel over and be like, wee. So that's a 0.00000000043. So very, very tiny, tiny p-value, equivalent to about 0. 3 decimals out, it is 0. Now, since the p-value is 0, that means we're going to reject the null. So we would reject the null and say that we conclude that there is evidence that the two are not independent. So the null is that they're independent, and we reject the null, and we conclude that there is evidence that they are not independent of each other. Check those answers. We've been on a streak now. Getting all the questions right. Haven't gotten one wrong in a while. It's so easy to make an error and click a wrong button. We do it all the time. But great stuff right here. Let's hop back to the main screen. What questions are there? What? Drop all those questions in the chat. Looking at the 320 or the 201, what you're saying. Oh, thanks. Kayla is talking about writing wing at the pure guns. Can we do students in an industry question? Yeah. Let me go find that one. I was replying to some Discord stuff. Wait, I just found it. Yep. All right, cool. We did this one earlier, but let's do it again. It's good practice. You ready? I've already selected the right answer. Let's do this. First one, we did this one earlier today, but don't worry. Good question right here, Vincent. Let's go do the question. Vincent, you're here. It's your office hours. You got this. Let's do this. So we've got students in an introductory to statistics classes and what they're majoring in. So we've got their birth order and the college of what they're in. Now, we do the chi-squared test of independence. We don't do the homogeneity or the goodness of fit test. So we don't do those here. Not happening. So state your hypothesis. What word goes between someone's college choice and their birth order, Vincent, when we do the chi-squared test of independence? We'd say that somebody's college choice is what of their birth order? Like, what word goes here? Like, when you're doing the chi-squared test of independence, if you're writing the null or you have choices, you probably want to look for something that would say the two things are what for the null. Like, you're like, okay, I got to write a null hypothesis. The null's probably going to be talking about how these two things are what of each other. Like, probably a good start would be to state that the two things are what of each other. Independent. There you go. 100 points right there. You got it. Great job, Harper. So let's see if anything looks like independent. Right there. There's the null. I'm on the same question. Perfect. Look at that. Harper, another 100 points. Harper and Vincent for asking a good question that people are both on. So choice of college is independent of birth order. So good stuff right there. So now this is where sometimes they trick you, because the best thing to probably write would be choice of college is not independent of birth order. But that's the same thing as saying that there is an association. So if you're saying they're not independent, independent means knowing one tells you nothing about the other. But then there is an association would mean knowing one tells you something about the other. So that literally means not independent. So they're trying to trick you. Not good. Now, this one right here is rather interesting because the smallest expected cell count would actually be these two cells. And so when we check the conditions right here, we would say, first off, is it randomly collected? No one forgets condition one. If they forget condition one, I'm very sad. Is it less than 10% of all students? Random also means independent. And then we ask, is it count data? But can anyone, I will throw 500 points. I know, Vincent, you're trying to get those points. So Vincent, tell me the amount of the lowest expected cell count and be careful. Take a moment here and find for me the smallest expected cell count. We will not pass the at least 5 for smallest expected cell count. And the answer is not on the screen currently. I mean, the formula, you can write the formula for it. But what is the smallest expected cell count? You're going to have to solve a formula, kind of like that, to find the smallest expected cell count, which will not be greater than 5. The answer is currently not displayed on the screen. We'll have to solve a formula for it to get the smallest expected cell count. Remember, expected cell counts are row total times column total over grand total. So the smallest expected cell count, and this is worth 500 points here. See if you can remember how to find the smallest expected cell count. What would we do? So what would be that formula? And there's actually two cells that have the smallest expected cell count. You say, but no, I see a 2. Well, that's an observed. That is how many we observed. We observed 2 students who were the third in their family order and are a professional. So there were 2 students observed in that group. So, but what's the smallest expected? It's for 2 cells because 2 of them have the smallest column total. So what are your thoughts here? What is, with 500 points on the line, what is the numeric amount of smallest expected cell count? So there's a skill we need to have. If I say, find me an expected cell count, you say, okay, I got to do row total times column total over grand total. So what would it be? Well, yes. So what is the numeric value of the smallest expected cell count? I'll show it here visually. So you have to solve the formula. Oh, no worries. So put the formula, I'll say it again if we need it, but what's the formula for the expected cell count? Let's go to the review sheet. We know this is chi-squared. Right now we're on the test, and it says, what is the smallest expected cell count for this problem right here? It might be that. I'm going to cheat and do it over here. Vincent, you might have got it. That's not the answer. Okay, Vincent, did Vincent solve it? It might be. Vincent, or Harper, 500 points. Harper, you are correct. Harper earning everyone 500 points in the chat right now. Harper is correct. So what did you do, Harper? You are correct, Harper. And so here's the formula sheet. The formula for expected cell counts is what again? Row total times column total over grand total. So if we want to find the smallest one, so it's row total times column total over grand total. We have it up there. We're going to take the smallest row total, which is this, and the smallest column total, which both of those tie, so it doesn't matter. It doesn't matter! They're both going to give the same expected, and then we would multiply. Does that make sense right there? Does that make sense, Vincent? Like, either one of those could be the smallest. Like, these both tie because the equation would be the same. So you would just solve exactly, Harper, great job right there. And so either one of those would solve the same equation. Like, you could, the other one will have the same because it has the same column total. Because the mathematics here for this one would just be that. 25 times 34, and the top doesn't matter which way you multiply. Technically, with row total first. Ditto, great to see you here. So Harper, great job right there. And Harper has shown mathematically that if you solve this, I'll just show it on the screen so people can see the solve. 34 times 25 divided by 233 is equal to 3.648. Now, why does this fail again, Harper and everybody? Why does that fail? Because it is not greater than or equal to 5. So they're not at least 5, so we do fail that condition. How many degrees of freedom does this have? Now, we got this. We've been practicing this. So this is a what by what right now. I don't want to show you the answer, but this is a what by what. Vincent, great work right there. This is the practice. So this is a what by what. Say, Brian, this is a blank by blank up there in that table, and thus the degrees of freedom formula is blank by blank. I think I know what you're getting at, Vincent. So the degrees of freedom are rows minus 1 times columns minus 1. So we have to start off by saying, Brian, that's a blank by blank table, and then we reduce it down, and then we multiply the numbers. So what do you think right here? It's a 4 by 4. So Harper, what are the degrees of freedom? Harper, you got this now. You'd be like super quick on these because we don't count the totals. So there's 4 here, 1, 2, 3, 4, and there's 4 here, 1, 2, 3, 4. Don't count the totals. So the degrees of freedom would be what? You just said it's a 4 by 4. The degrees of freedom are going to be what? So it's a 4 by 4 table. Don't count the totals. There's 4 colleges. So Harper solved the equation 3 times 3. It's rows times 1, rows minus 1 times columns minus 1. There's 4 rows, 4 columns, minus 1 on each, 3 times 3. So there was 4 rows, 4 columns, minus 1 on each. 3 times 3 is 9. So great stuff. Another way, and this might help people, is to think about it visually. You can actually visualize the degrees of freedom. Now, be very careful if you do this. You don't want to use the totals. But check us out. Taylor, do you mind explaining how to solve one? Yeah. Yes. So I'll go talk about that next, Taylor. Yeah, I'll kind of allude to it. I don't want to quite give away the answer, but I'm deleting 1 row and I'm deleting 1 column. So Harper, do you see it? If I delete 1 row and 1 column, how many values are inside of here now? Oh, no worries. No worries. A little tricky. It's a little tricky. The interaction one's a bit crazy. If I delete 1 row and 1 column, then what do we get right there? So do you see there's 9, which is the 9 right there? If you delete 1 row or 1 column, you get 9 right there. So you can do it that way visually too. Just don't use the totals. I've showed that way before, and I fear a lot of people actually use the totals, and then they say there's 16 degrees of freedom. So I've seen that common mistake when showing it this way, and so I'm a little hesitant, even though I just did it. The p-value is 0.00065, 0.0065. And great job right there, Harper. So would you reject or fail to reject the null here? Just the p-value is less than alpha. So with a p-value less than alpha, reject or fail to reject the null hypothesis. With a p-value less than alpha, reject or fail to reject the null. What do you think? So p-value is lower than alpha. So we are definitely going to do what? P-value right here is way less than alpha. That means for certain we what? Like it's like, you know, sometimes you're like, oh, p-value is less than alpha. Boom, do this. It's how we roll when it comes to statistics. P-value less than alpha, we are going to reject. Yeah, because there is evidence. Yep, exactly. We reject the null. There is evidence of an association between the two. Exactly. When you reject the null, it's because you're convinced of the alternative. Not saying the alternative is true, but we just have good evidence to believe the alternative at this point. Now, this last one right here talks about residuals a little bit, but the big thing is they're just pointing out that the expected cell counts had a condition that they are not meeting the condition, rather. So that's the key with the last one right there, is it's harping back to your results are kind of suspect right here. So like, a little worried about the results. Don't worry about the idea of standardized residuals. We will not say the word standardized residuals on the test. It's literally just saying your results are iffy because you violated a condition. Good stuff right there. Let's hop back to the main screen. We're going to talk some 320 right here. Those first two questions are a little tricky. I put an extra exclamation on one of the 201s. I should go look at completion percentages after this. Do I still have the quiz up? Where's the quiz at? I got too many tabs open, but what's new? What did it do? Oh my gosh, sorry, yawning on stream. Oh man, you think after break you'd be wide awake, but it's like, oh man, dealing with so many things. So many things. That's the way life is, right? Life is just a bunch of things, and you deal with them as the things arise. And you delete the page you're on, or you click away from it really quickly. Here we go, activity preview. The first one's more easy. I don't want to solve it out exactly. Let me see here. I'm going to solve. I don't want you to see it though. Let's see how quickly I can get these, because I've got the formula. I might go through the first thing we did again. But the second one's tougher. Let me see how I get it. Did it work? Submit. Didn't answer all the other questions. Yep. Good stuff. Okay. Let me remove this off the screen and talk about this. So the first two questions. Okay. Let's go check out the first two questions on BAS 320 and let's do it. Okay. So the first two questions are related to when you're looking at all possible models, how many models would you have? And what's really great is we basically give the equations here, but you have to understand theoretically what you're doing. When you have a data set like the customer loyalty data set, the customer loyalty data set has in it, let's clear out the environment. It has one Y variable and has a bunch of X variables. And it's important we think about how these variables exist. When we have, that's actually the data set we want. Let's start from scratch though. When we make models, our model will have one this variable. Our model will have one this variable, which we don't need to consider. I'm actually just going to blank it out this time. When we make models, our model will have how many of this variable? One of it, rather. So our model will have only the thing we're trying to predict. And what variable is that? We're trying to predict customer loyalty here, right here. Customer LV. Lifetime value, rather. I'm going to blank it out because that's the what variable. That is the Y variable. So that I'm going to make it so we don't even see it anymore. We will use it, but it's not an X variable. Does that make sense, Taylor, right there? Yep, one Y variable. So I'm just going to remove that because that's not part of the X's. So there's really two types of X's we include in our model. One type of X we're considering right now is a quantitative, and the other type of X, which might require a little more attention, is a what type of X. So we have quantitative X's right here, and so these are quantitative X's, and so that's a quantitative. So those are all quantitative, and then the other X's could be what, which you see as factors inside of R. So we have quantitative X's, and then we also have what other types of X's? What other types of X's? Categorical, exactly. It really boils back down to 201. I try to tell 201 this all the time. I'm like, everything you're learning right now is used in all the other disciplines. Like, it's very important that like you get the basics down. So when we introduce categorical variables, they will have a default level called this, and then they'll also create indicators. So they'll have a default level called this, and then they'll also create indicators. It's categorical because it's all count data. It'll be categorical because two categorical variables make chi-square test of independence. Good question, Vincent, right there. So every single test in 19 uses two categorical variables. So it's all count data. That's the count data condition. We're talking about variable types right now in 320. So every single X variable introduced as a categorical one will always have a default level called this, which other levels are compared to. We call the things that are compared to it indicators to indicate their difference from the what level. So there's always one of these for each one of them. Like gender will have a this. Married will have a this. Reference level, and it'll be the first alphabetical. So you can actually see right here, the reference levels are going to be these. They don't get indicators. So these are all the reference levels right here. They're the first, and then everything else would get indicators. There's going to be more indicators over here. How many indicators would there be for, let's say, something like gender? So if you look at gender, how many indicators will gender introduce into the model? So how many indicators will gender introduce into the model? So how many indicators will gender create? Which we actually have it displayed properly on the screen right now. It's only one of these that is a little not properly displayed because you can't see it all. How many indicators will gender create in the model? And you have to look how many levels there are. And remember that one of them goes to the reference. So gender will create how many indicators if it goes into the model, like preserving model hierarchy. If we put gender in the model, gender can create up to this many indicators. So what would that be? Because it has two levels. One of the two levels goes to the reference level. So how many indicators can it create? Because it has two levels. One of those becomes the reference level. And then it would create then how many indicators? So there's two levels. And one of them goes to the reference level. Like this is the one right here going to the reference level. It goes away. So how many indicators would gender create? One. And so that right there. And it's the same thing for this one right here for married would also create one. But then this one's interesting. It has 6. So this one has 6. So how many indicators will it create when one of those, which F0 to 30 is going to go to the reference level, then it would create how many possible indicators? Because F0 to 30 is going to go to the reference level, not create an indicator. How many possible indicators are there for this one? This is a hint for the assignment. This is a 6-level categorical would create how many indicators? Kind of one of the key things to know. A 6-level categorical would create how many indicators? So this is like a key component to solving the question you're trying to solve. A 6-level indicator would create how many indicators? Or 6-level categorical, 5 indicators. 6-level categorical would create 5 indicators. Now, a quantitative variable just introduces with it 1. That's a 2-level categorical. So a 2-level is going to introduce 1 because the one goes to reference, the other becomes indicator. This is 1, 1, and 1. So we have 4 quantitatives. We have 3 categoricals that are 1 level that introduce 1 indicator. And then we have a 1 categorical that introduces 5 indicators. So the answer is going to be how many? Tell me a little off. Oh, 3. There's 3 of those. So this has to be times by 3. That's why. So this should be 12. If you add up these numbers right here, I'll highlight them. These numbers right here add up to 12. Just make sure I tricked myself even because you'd have to times that by 3 because there's 3 1-level categoricals. So that makes sense that there are 12 possible X's / coefficients that could be created. How are you doing with this right here, Taylor? Each of the quantitatives introduces 1 indicator. The categoricals with 1 level can introduce 1 indicator, and there's 3 of them. And then there's the 1 categorical with 5 levels. So this right here would indicate to us that there are 12 possible right here. So the K is equal to 12 right here, which is the number of predictors we can introduce, found by the 4 plus the 3 plus the 5. The 3 is 3 times 1 rather, because it'd be different if there was more. But the 4 plus the 3 plus the 5 is going to be this right here. And specifically, 1 times 5 is 5. And so maybe I should underline that. 1 times 3 is 3, and 1 times 5 is 5. So this is equal to 3, and that is equal to 5, because that's how many it'll reduce. And this is equal to 4. So that's got that right there. That's 12. How does it change when asked with or without it? Ah, yes. So, well, this is just how many X's there are. This doesn't do with how many models there are. So now that we know how many X's there are, so all we found is just, it's like I'm asking you to make a soup. So here's a soup, and I'm giving you 12 ingredients. So now the question becomes, let's say I've got soups for you. I want you to build a soup right here. I think this might help with it. I have a soup with 12 ingredients: potatoes, chicken, garlic. I will even do this: salt, pepper, cheese, beef, let's say mushrooms, onions, peppers, let's say celery. I just want some soup. And do we do peppers? We did peppers already. Scallions. So I spell scallions? Cool. Make your soup. You have 12 ingredients. So, no, that's all right. So you have 12 ingredients. I just want you to make a soup right here real quick, because hopefully this will help. Make a soup for me real quick. I'm going to make you a potato, onion, pepper, mushroom. My soup is going to be the following. I'm going to choose my soup right here. You can just toss them all in the pot, Brian. Here's Brian's soup. What is your soup going to be? Yeah, this would be a good soup right here. Oh, you got to put the cheese in. You go crazy. Do we put peppers on here twice? We got a green pepper. Let's say G pepper and red pepper. Green peppers and red peppers. There we go. Just to make it. So now we got green peppers and red peppers on here because we got peppers twice. And there's the cheese. You got to put cheese in. We already got a little bit of salt on there. Oh, I meant like pepper, like salt and pepper, not peppers. Yeah, so that was the regular pepper. What am I doing? So this is like salt and pepper, not peppers. That's obviously peppers. Obviously. I think... Yeah, put a little chicken in there. It all sounds good, doesn't it? There's my soup. Yeah, we'll do one next to it. You got it, Vincent. This is my soup. But someone could just actually not even want soup technically with this. Does that make sense? There are tons of ways to make this soup, and that's what we're about to do. We have 12 different components. That's what we're looking at here. Here's the 12 different components that can go into this soup. Here's the soup we got right here. So my soup is this. I'm just deciding this is my soup, and your soup could be anything you want. So now what do we say are all the combinations of soups? Well, to find, since we know K is 12, if we want to look at just putting the things by themselves in the soup, we would have a 2 to the 12th possible way of making soups. So 2 to the 12th right here is going to be just 2 raised to 12th. I would have 4,096 combinations of soups to make. Does that make sense, Taylor, right there? Like, the ways in which people could make all the different soups right here are 4,096. That is the ways in which I can make every single possible soup. So it's just 2 raised to that. 2 raised to the amount of soups we could make, the amount of items. But then, if we allow for interactions, like we somehow like splice them together and we're like, well, now they can interact, which really doesn't work with the soup analogy, but this is allowing for an interaction between the two things. Like we have some sort of like where we interact the pepper with the salt or something. I don't know how to do that. So that's without the interactions. You're right. That's no interactions. It's going to get crazy here with the interactions. So now with the interactions, this won't work as an equation yet because it's not written as one. Now we need to add in a multiply right here. You just can't take that as is normally. We're going to say K equals to 12, and there's the with interactions. Now, if K is not as crazy, you don't get as crazy of numbers. You just can't have K be insane, because as soon as K gets to like 20, it's just going to say like, yeah, you're insane. Then we probably don't even have a good way of entering that in. But yeah, if you do K200, it's just going to say infinite models. Because, I mean, there is a number that exists. There is a certain amount of models, but I'd be shocked if we can even go up to K50, because it's probably just going to go infinity on that. You reach what the computer would consider infinite models rather quickly, and this is only with this many predictors. The computer eventually just says, nah, that's too many models for me to even talk about. Looks like it might go to 300 zeros. There is actually a thing to compute really big and really small stuff inside of R, so you could maybe get a computation on something, but your computer's not going to be able to make a half a Googleplex or something of models. Does that make sense right here? So using that formula right there, we can just plug in the K, and the K is just how many predictors we have. So if you know how many predictors you have, you can do a computation to see how many models would be created. For smaller amounts of k, like k equals something like 5, you would have 32 possible models. If you include interactions, you'd have 32,000. So if you notice right there, there's a huge exponential growth going from just looking at each different model, like 5 different items we can put in our soup. There's only 32 combinations of soup, but you fill out for interactions, you have 32,000 combinations of soup. So where are you getting the 30 from? Where's your 30 coming from? So it says 2 numerics and 1 categorical with 4 levels. Where's the 30 coming from? So go through the process. I don't want to question and answer, but go through the process where you look at your quantitatives and categoricals and find out how many they introduce. But the 30 is a little bit of an issue. Well, so you might have multiplied. Remember, so how many coefficients does each quantitative introduce into the model? I don't want to quite say the answer, but how many coefficients does each quantitative introduce in the model? Each quantitative introduces how many coefficients? Like look at the work up here. Each quantitative will introduce how many coefficients into the model? Every single quantitative will introduce how many coefficients? Because mine has 4 quantitative. One. And then you have 1 categorical with 4 levels. So if some categorical has 4 levels, how many will that introduce into the model? So a categorical with 4 levels would introduce how many into the model? So a categorical with 4 levels would introduce how many? You might have an OMO. You're like, oh, I got it. So I don't want to quite say the answer, but just think you have 2 quantitatives and you have a 4-level categorical. So your data would look something like this. Like think about how your data would look. You collected data on height, weight, and both of these are quantitative. And then your other one would be something like a 4-level categorical. You do class level is a 4-level categorical. So here's what your data would look like. You have these X's. I'm not saying these are your X's, but sometimes it helps to visualize. And then you have to be like, okay, how would this work when I look at the, how many coefficients am I going to get out of this? Is that making sense right here? What your K would be for this? How many possible X's could be included? So you have you have 2 quantitative variables, which are just numeric right there. And then you have a 4-level categorical variable like freshman, sophomore, junior, senior. I can't quite say, but I don't really have comments on that, if you get what I'm saying. Is it making more sense, Taylor? Like, I'm not saying anything, but, since I'm not saying anything, can't wink. I didn't wink. I didn't tell you the answer. But is it making more sense right here what's going on? I think seeing possible data sets might help out to be like, okay, when we say 2 quantitatives, we mean this. When we say a 4-level categorical, this is a hypothetical 4-level categorical. I think these things right here can make more sense. Yeah, great job, Taylor. 100 points right there. Keep it up. So it should make more sense. Once you know the K, it just goes to solving a formula. Like it's just formula then. It's just plug formula, solve, answer. Pretty crazy. Did I do? Oh. I didn't know your question, but hey, make sure to be careful on the interactions and the non-interactions one. Good way to make an error is to not have the right interaction one. So if you don't choose the right interactions, I think we're gonna do political party next. Political party. Let me get that up and going. Political party. And thank you, Taylor, so much for swinging by. I'm gonna really try to tell 320 next semester, come by office hours. I'll help out. We'll go over the topics. Could you do the gender and political party? You bet. Gender and political party. I am so tired. How am I so tired? I'll wake up one of these days. Just gonna watch all the streams of me yawning. Busy times. Get ready for the end of the semester. We'll all sleep after that, and we'll have a great Christmas break or holiday break, whatever you celebrate. But anytime, Taylor. I'm glad you appreciate it. Really glad to have you here. Good stuff. Let's continue on right here with the gender political party question. Let's do it. Is this the homogeneity test or the chi-square test of independence? Well, there's only one we do, and that is the chi-square test of independence. So quick and easy question right there. Homogeneity looks for homogeneity between the groups. We're not doing that right here. Are you telling the BS 474 project questions? I can talk about it, Edgar. And thanks so much. I know Edgar had some Discord messages. Do you have questions about it? Feel free to post them. I can't go into too much specifics, but I can kind of talk a little bit about it. Have you done the poll classified respondents? I think we just did that one earlier, Destiny. I think we did. Yeah, let's go find that. So Vincent, we might need jump for this. We might need jump. So I know you said you might use jump later. Destiny, we could do it again here. I think we got enough time. We'll be on off hours here in just a little bit. But Destiny, thank you so much for swinging by. 100 points Destiny right there. Edgar, post your question. I'll see if I can answer it. So what do we always put right here? What's our easiest way to talk about gender and political party are what of each other? Like, what is our number one quick and easy solve to put between for the chi-squared test of independence? What do we put, like, what do we look for? Something that would say the two are what of each other. Not every one of them will say it, but we should know this word means that there's nothing going on. Like, you know this, it tells you nothing about this. So the name of the test in itself gives us a hint that we should look where it says something about gender or political party and gender are what of each other. This one's nice. The chi-squared test of independence has the null hypothesis that the two are independent of each other. Just remember the test you're doing. I'm doing the chi-squared test of independence. Vincent gets right there, another 100 points. Vincent is, we're going to say the two are independent of each other. So we're going to go here. Political party is independent of gender, and the alternative would be they're not independent. So D, great job. About deciding class of some variables that are either have a which data set are you working with? We might have to talk on Discord over this. Mubot, Edgar, I'm gonna go out here and say you're a mod. If you want to repost that message, Mubot he saw symbols, so he was like, I don't know what you're posting. People can make like certain like ASCII art with symbols, so he might be thinking, oh, what you doing? But I trust you, Edgar. You're now a mod, so you shouldn't have problems with Mubot getting mad at you right there. Are the conditions satisfied for this test right here? The count data means that we have categorical. Good stuff right there. Randomization. For some variables. You're talking about and which data set are you working with? Randomization means we randomly select these individuals. Yep. Expected cell count. This one we're actually going to hop over to jump and pretty much solve the rest of the problem with. So we're going to go over here to copy to clipboard. So when we copy this to the clipboard right here, let's go ahead and take it. And we're going to hit Control-C or Command-C on this. And once we copy it, we're going to go down here to jump, and we're going to open up and go to File, New, Data Table. File, New, Data Table. With File, New, Data Table, let's go ahead and click it. We're going to go to Edit and make sure you do Paste with column names because it had column names in there. Pause right here. Let's see. You might have to do like a combined levels on it. I don't think which data set that is. Flash for some variables. I think you're talking about an X or something. So you might have to do a combined levels on that. If they have very low occurrences or they're, like looking through your data. So now we're going to go over here to tables and we're going to go to stack. I'll pause here again. Tables and stack. Table stack. We're going to take the D, R, and I column and stack them on top of each other. How do I use the equation to be all cells of my? That is correct. So that is correct right there. So what we're doing right here is we're basically setting this up, Vincent, right here, because when you do this, and here I'll show you one of them, because do you have all your expecteds, Vincent? Because if you're doing it in jump, you can go right here and go to Analyze, Fit Y by X. And when we go to Analyze, Fit Y by X, we're going to put in, I'm pretty sure this one goes here. Just going to make our table look like theirs. And now we're going to put the frequency in here. So now we've got all the data in, the Y, the X, and the frequency. And let's go ahead and click OK. And we see right here, I think this is the way they have theirs set up. No, they have it reversed. So I'm just going to flip it real quick just so we can see the exact way they have it. So let's go to I didn't want to do that. Let's go to redo, relaunch, and let's switch these to down here and there. And now let's take a look at these. So how do yep. And so what you start out with here is the counts of the observations. Does this make sense here, Vincent? I didn't want to click that yet. Here are the counts of the observations. This is just how many people are in each group. So if you notice, oh wait, we still have it over here. This is how many people are in each group. How are you doing with that? Like it's got male and female reversed right here, but there's 40 males who are Democrats. There are 42 males who are Republicans. It's a little bit differently ordered, but we have each of these right here, like the counts of the individuals. Now, what we want to find is all of the expecteds. To find all the expecteds, we do row total times column total over grand total. So you wouldn't find the p-value. You can find the expecteds and the observed. That would be found. So this 39.4203 is going to be row total times column total divided by grand total. And that's how we get that value right there. That was row total times column total over grand total. Does that make sense right there to get the expecteds? How are you doing, Vincent, right here on the expected values? Like this one right here, this 21 would be 96 times 46 over 207. The row total for it times the column total over the grand total. So to get this one, we do 96 times 46 divided by 207. And that is that value there. How is this looking? You can get all the expecteds. Once you have all the expecteds, we then find, and you're on this step right here, find the cell chi-squareds. So the cell chi-squareds are the observed minus the expected, squaring that value over the expecteds. So observed minus expected squared over expected. And that is each cell chi-squared. How are we looking, Vincent? Give me updates on this. How you doing? How is it looking on finding these values? If you do all this by hand, you have to write each one down and solve each one to get each expected, to get each cell chi-squared. So you have to do each of these steps. So now it wants the chi-squared, right? So how do we get this chi-squared value here? Once we get all the cell chi-squared, so you want to get to the point where you have every single cell chi-squared. What do we do to get the chi-squared test statistic? So let's say you found all the cell chi-squareds, which is what we want to do. And we did a big walkthrough example problem earlier today on this. If you do all the cell chi-squareds, what do you do with your cell chi-squareds to get the chi-squared test statistic? Good theory question sometimes on the test. To get the chi-squared test statistic, you take all your cell chi-squareds. You're welcome, Harper. Great job right there. Another 100 points, Harper. To get the chi-squared test statistic, you take all the cell chi-squareds and you do what to them? So once you find all your cell chi-squareds, you would then go to you would do what with them? You would sum them up. You want to add all these up, and that's going to give you the Pearson chi-squared test statistic. If you add up all the cell chi-squareds, you get the Pearson chi-squared test statistic. Remember, Pearson's where you do your work, so it's a good way to memorize, like Pearson, that's where I would do my work, Pearson chi-squared test statistic. So the Pearson chi-squared test statistic is 3.196. So it wants all those decimals. That's the Pearson, and we meet all the conditions right here. Yes, we meet that. So 3.196. Now the p-value, we have to go and plot this. So we have to go to the chi-squared distribution right here to plot this. So Vincent, this is a 2x3. How many degrees of freedom does this have? So this is a 2 rows, 3 columns. How many degrees of freedom will this have? So I need to know the degrees of freedom before plotting this value right here. How many degrees of freedom will this have since it's a 2x3? It's 2x3, so it'll have how many degrees of freedom? 2x3 means how many degrees of freedom? So maybe you go 2x3 and you reduce. So how many degrees of freedom? 2x3. So if it's a 2x3, 2x3 reduced by 1 each, 2 degrees of freedom, because 2 times 1. So we're going to go here to 2 degrees of freedom, plot the chi-squared, and get the p-value of 0.202, which we also have in the jump output. The jump output over here shows us the p-value of 0.202 right here, which is the same p-value we see at 0.202 right here. And that's going to do it. That's going to be the p-value. And it's a very high p-value. So we fail to reject the null. There is not evidence for the alternative. We do not reject the null. There is not evidence for the alternative. Very, very high p-value right here. And so we've got it right there. That's got it. Any other questions? Let me know, Vincent, how you doing? Let me know, and let me hop over here, see what people are saying on the Discord. Hop into the main screen. Yes, let's see what Discord's saying. Aw, people are saying such nice things. All those nice things on the Discord. Let's see. Awesome. Which one did you want, Griffin? Oh, the war question. We did a war question earlier. Let's see. Let's do the other one. Let's do the other war question here. Thank you, Griffin, right there. Okay, I think we got the other war question up. Does one still have an error? Yes, it does. They've got an error on my Pearson. You're welcome, Vincent. Great work getting close to those points. Keep getting them up right there. Let's go do the last war question here. Then I'm going to head off, grab some lunch. Woo! We've got a certain war story, the other war story, about people getting injured and what they got injured by. So it says limb right here on this other one, but I don't think it's limb. It's the arrow, ground rock, or it is a sword. My Pearson, you got a typo on your site. So I think I made a typo when I did this one last time too. I got an error or something. So a certain war story. We did the other version of this. They're the other version. If you're looking for the other version, it's earlier on in this video. Check out. There'll be a timestamp later. So what is our null hypothesis for the chi-squared test of independence? So Griffin, what is the null hypothesis for the chi-squared test of independence? That the two things are what of each other? So if we were to talk about the site of somebody's injury and the weapon, we would say those two are what? This one is nice and easy because they use our format that we love so much. The two things are what of each other? The site of somebody's injury and the weapon would be what of each other? Chi-squared test of independence. So when you start off, you would assume that the two have nothing to do with each other, that they are what of each other? So what would we assume? The site of injury. Great job, Griffin, right there, 100 points. So we're going to assume they are independent, and the alternative would be that they're not independent. So I really like the way of writing it like this. Watch out, they will say things like they are associated for the alternative, or you could say they're not associated here. Synonymous words, good to know. Now this gives the expecteds right here. So we're going to make our life easier and do this inside of jump right here. So we're going to go over here and go to copy and copy to clipboard. Class in 30 minutes. So we're going to copy this to the clipboard right here. Copy. And we're going to hit copy, copy, copy. And then we're going to go over to jump. Scroll down a good bit to our millionth jump data sheet. And go to file, new, you know where we're going, data table. So file, new data table. Great to see you here, Andrew. File, new data table. Under file, new data table, we're going to full screen it to begin. And then go to edit and then paste with column names. Paste with column names. So now when we paste with column names right here, we get the data table in here. But now, we'll pause right here, make sure everyone's got that edit paste with column names going. Now we're going to go to tables and stack these columns. We're going to take both those columns there and stack them. We've got this stack, the quantitative columns, body / head, neck, and limb. So let's wait for a moment right here. Tables, stack. So let's click to tables and stack, and then go to body, head, neck, and limb. And now we have those right here. So we're going to take these, good to see you here, Madison, and we're going to stack these right here. These are the three quantitative columns, and they'll be stacked. Let's click OK. And now that we have this, we are simply going to run our analysis. Let's start on some 100 points, everyone hanging out here today. So we're going to go to Analyze, Fit Y by X. And with this, it's going to be kind of important which way we do it. I've not lucked out on the ways earlier today. We're doing a categorical analysis, which is going to give us the contingency table. And make sure you put the data in here. This is key. You need to have the data right here as the frequency. That tells us how many counts there are. Those are the literal counts of the observations. And let's see if we have the correct way of viewing the table right here. So I'll pause right here. Make sure you have all three of these things in the proper order. Is this the proper order? Yes, it is. And I hope, yep, I think this is going to be correct. Let me look. So arrow, ground rock, and that is sword, even though it says limb. Thank you, my Pearson. Body, head, neck, and then the last one over there is limb also. So our table is the same way. So if you do this by hand, it would actually take quite a while. It's much easier to go in here. We're just going to remove everything for time being. I'm unchecking all of these. So we want to get our own table right here and get the expecteds. These are the row totals times column total over grand total. And so we can get all these values right here. I wish I could just copy paste that whole thing, but it won't let me. So these are all of the expected counts for how many individuals we would expect by random chance to have these sorts of injuries. And I'll disappear off the screen so you can see the numbers as we enter them. Just make sure to be very careful to 2 decimal places. Very easy to make mathematical errors. And this is why we use software, because it's way easier than solving all these by hand. Check out the earlier video today where we worked through, ooh, that's a violation of the at least 5 on all of these, or almost all of these. Check out the earlier video today And please say something if I make a copy error, because I think it's very exact on its rounding. I think we got it. 5.42, 3.78, 2.79, 4.52, 3.15, 2.33, 56.05, 39.07, 28.88. That's got it right there. So those are all the expecteds, but now we want the chi-squared test statistic. The chi-squared test statistic is the sum of all the cell chi-squareds. So we'd have to go here to the cell chi-squareds. And with the cell chi-squareds, if we find them all with the observed minus expected squared over expected, summing them up would get 21.955. So this one right here, 21 point, says 2 decimals, 21.96 is going to be the 2 decimals. The degrees of freedom is the easiest one to calculate. I'm going to pause right here because this is the one we don't really need calculators for. The degrees of freedom is going to be what? This is a 3 by 3, so nice and easy. Degrees of freedom is what? This one, if you see it on the test, you're like, free points. Free points right there. We like that. Who knows, since this is a 3 by 3, it would have how many degrees of freedom? This is free points, and we love that. We love those free points. 3 by 3, because there's 4. Griffin, great job. And so there's 4 degrees of freedom because there's 3 here, there's 3 here. 2 times 2 is 4. Rows minus 1 times columns minus 1. So that is excellent stuff. That is good stuff. And now, last but not least, the p-value, which is basically 0, but it's not. How many decimals? 3 decimals. The p-value over here is 0.00002. So that is going to round to 0. Very close. I'm a little worried on that one, but it is 0, according to the rounding. And so now we go over here. What should we conclude? The p-value is basically 0. Reject that null. There is evidence, so there will be evidence. We conclude that there is evidence that they are not independent of each other. So you better, getting scared. Last question of the day and getting scared. But there is very strong evidence. And you can see it in the plots also, that if you go over here to the plots and you look at it, the people are being injured more often by a sword in the body, where the ground is injuring more of the head. And it's kind of a bummer you fall on the ground. Arrows are hitting more limbs. So arrows really hit people in the limbs, where the ground is hitting people in the head and the neck. And the swords are going to the body, but also some distribution of head and limb. But you can kind of see the differences where people are getting hit with certain weapons. And it seems that there is some sort of association that the weapon you are hit by, or the part of your body you're hit by, is associated with what weapon hits you. Like, oh, you got hit in the head? Well, you might have hit the ground. Oh, you got hit in the body? Probably likely you got hit by a sword. Not saying you did get hit by a sword, but the body injury is more likely given a sword. So given someone got hit by a sword, more likely a body injury. Given somebody got hit by an arrow, more likely a limb injury. So that's got it right there. Definitely evidence of a pretty strong association between the weapon someone got hit by and where they got hit. One of our last office hours, we're having office hours tomorrow, though. We'll be finishing up. And then we're going to do some Kahoots. So get ready for all those Kahoots. Until then, I'm going to go grab some food. You should too. Class starting here soon. Bye for now, everyone. Bye. See you soon, everybody. Which one was it, Edgar? Can you message me on Discord since it's like 474 projects specific? I think you're asking, you'll have to tell me which data set. I think we're talking on Discord, right, Edgar? You're asking about okay, so I'm having trouble into how to decide about a class for some barrels that have either, you're talking about the class of it, like is it quantitative or categorical? Well, so it probably is going to be categorical, right? I think, were we talking about this on Discord? Let me go look at our messages. Here we are. Yeah. No, it's probably going to be categorical. Oh, I see what you're saying. The experience, right? Yeah, that's going to have to go into categories. That's going to have to be converted to categorical. Because but it says greater than 20. So, since it's greater than 20, it has to be like the 20 plus. Does that make sense, Edgar? I didn't see that. I saw the message on Discord now. So every character version. Probably. Well, yeah, a lot of these are going to be basically you want to go through and look at it. You also want to look at the documentation. How's that? Is that making more sense, Edgar, right there? Like, going through the documentation, looking at this, looking at the data set to see, especially with experience, that's going to have to be categories. And then the company size, that has to be categories too. Because, yeah. So does that make sense right there, Edgar? I think it might be good. But yeah, you'll have to convert those right there to probably factor class. Awesome job, Edgar. Great work on this. I think that's got it. Thank you so much, Edgar. Thank you for asking about that. But yeah, message me on Discord since it's like project specific. We'll probably talk more about it. But that's got a great job starting early. Lots of work to do. Probably factors. I'm gonna reply. That way I think. Replying here too, to not forget that I replied. I don't want to be. Sometimes I have a lot of Discord messages like, whoops. Well, that's got it. We'll be back. 475 starting soon. Bye for now, everyone. Bye.